Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss law of equipartition of energy, degrees of freedom and specific heat of gases. Let's begin. First, we see law of equipartition of energy. We see only the statement regarding law of equipartition of energy. Statement given as, which states that the total kinetic energy of a dynamical system, total kinetic energy of a dynamical system consisting of means that dynamical system consisting of a large number of particles and these particles are in thermal equilibrium. Thermally equilibrium, and these are equally divided equilibrium, and these are equally divided among all the degrees of freedom. And the average energy associated with each degree of freedom is equal to half kT, where K is the Boltzmann constant and T is the absolute temperature. This is the statement of law of equipartition of energy. Means the total kinetic energy of that of dynamical system, the dynamical system which is consisting of large number of particles, and these particles are thermally equilibrium, that means is equally divided among all the degrees of freedom, and the average energy is associated with each degree of freedom. The average energy associated with each degree of freedom means each degree of freedom have the energy is half kT, whereas K is the Boltzmann constant and T be the absolute temperature. This is the law of equipartition of energy, how energy is equally divided among all the degrees of freedom. Then question arises, what is degrees of freedom? So let we have to discuss degrees of freedom. Here we take the dynamical system. So what should be the degrees of freedom? Degrees of freedom for a dynamical system. So how we define? We say the total number of independent coordinates, the total number of independent coordinates required to specify why that these coordinates are required to specify completely about the position, and configuration of a dynamic system, is called the degrees of freedom. It's called the degrees of freedom of the dynamic system. And the degrees of freedom of the dynamic system means the total number of independent coordinates required to specify completely about the position and configuration of a dynamic system is called the degrees of freedom of that dynamic system. Taking an example to understand what is the degrees of freedom. Let you take the translatory motion of a particle. Taking the translatory motion of a particle. Translatory motion of a particle in any direction. That means that translatory motion of the particle in any direction can be resolved to the three coordinate axes, that is x, that is y, that is z. The direction is resolved are taking the parallel to these three axes x, y, z of that of coordinate system, and thus it requires three coordinates to define its position. Translatory motion of particle required three independent coordinates to define its position. Hence, its degrees of freedom. Its degrees of freedom will be 3. Means 3 independent coordinates are required to specify its position. That's why its degrees of freedom will be 3. Then another example. let we take a rigid body of finite size, a rigid body having finite size body is rotated, in rotation. Here we take both translatory motion as well as rotatory motion. Translation and rotation is carried out in this particular example, that is rigid body rotation. Since rotatory motion, if we take the rotatory motion, that can be resolved like translatory motion in three components, as we discussed here, three components which is perpendicular to that of xyz axis, and the state of rigid body now require three independent coordinates to describe that of translatory motion and three independent coordinates required for that of rotatory motion. That is why combiningly this, there will be 6 number of independent coordinates are required, 3 due to translatory motion and 3 due to rotatory motion. So here its degrees of freedom will be 6. Why? Since 3 due to translatory motion and 3 due to rotatory motion. In this way, 6 independent coordinates are required to describe its configuration or its position of a rigid body when it is rotated about that of axis. For rigid body rotation, the degrees of freedom will be 6. Now taking another example, if we take a monoatomic molecule, for a monoatomic molecule means one atom, example as helium, argon, etc. are the monoatomic molecule. So here what should be the degrees of freedom? Look at that monoatomic case. It consists of a single atom. Its translational motion can take place in any direction in space. Its translational motion is just like that of translation motion of that of particle in any direction of space. This can be resolved like this along the 3 coordinate axes as x, y, z, and this requires 3 coordinates to define its position, hence its degrees of freedom will be 3. So its degrees of freedom will be 3 for monoatomic molecule. Next, for a diatomic gas molecule, what should be the degrees of freedom? Taking for a diatomic gas. Diatomic gas example H2, O2, etc. are the example of diatomic gas. So here what should be the degrees of freedom? This diatomic gas consists of 2 atoms that are joined rigidly to one another through a bond. Let us take, here is the coordinate axis x, y, z. We take 2 atoms, one atom is here, one atom is there. and these two atoms are joined with a bond, and it cannot only move bodily but also rotate about one of the three coordinate axes x, y, z. However, its moment of inertia about the axis joining the two atoms is negligible. The moment of inertia about that axis is negligible as comparison to that of about another two axes. Hence, it have only two rotational motion. One rotational motion is there and another rotational motion is there. The diatomic molecule has two rotational motion and three translational motion. In this way, it required 5 degrees of freedom. Here for diatomic molecule has 5 degrees of freedom, 3 with respect to that of translatory motion and 2 with respect to that of rotatory motion. So, it has degrees of freedom will be 5. This is 2, 3 due to translatory and 2 due to rotatory. 3 due to translatory motion and 2 due to rotatory motion here, but that is neglected. Again, what should be the degrees of freedom for triatomic molecule, gas molecule? So, for a triatomic molecule, example as H2O, 2 hydrogen, 1 oxygen atom. So, the total atom are 3. Carbon dioxide, CO2, 1 carbon, 2 oxygen, etc. under the category of triatomic molecule. In case of this triatomic molecule, they can rotate about any of the 3 coordinate axes. As you take the coordinate axis here, x, y, z. Here you take the triatomic molecule, 1 atom here, 1 atom there and 1 atom there. So, we joined it. In case of triatomic molecule, they rotate about any of the 3 coordinate axes. Hence, it rotate either that way, either this axis or that axis, means 3 due to rotatory and 3 due to translatory, means the degrees of freedom will be 6 here. So, its degrees of freedom is equal to 6. Three due to translatory, 3 due to translatory and 3 due to rotatory, 3 due to rotatory. In this way, it has 6 number of degrees of freedom. So, in this way, we define what is law of equipartition of energy and degrees of freedom, and various examples related to degrees of freedom. Now, we have to calculate what should be the specific heats of gases. Specific heats of gases. let me consider one mole of an ideal gas. Ideal gas, which obey ideal gas equation, and that ideal gas at absolute temperature let T, and it has n molecules. It has n molecules. N molecules means where n is the Avogadro's number. Where n is the Avogadro's number. And since there is no force of attraction, between the molecules of an ideal gas, since we consider ideal gas, there will be no such force of attraction between the molecules. There is no force of attraction between the molecules of an ideal gas. Hence, there is no internal potential energy. Since there will be no such attraction, so there will be no internal potential energy. Hence, there is no internal potential energy. Therefore, the internal energy of an ideal gas, the internal energy means the kinetic energy plus potential energy, but here there will be no internal potential energy, means potential energy will be 0. So, only due to that of kinetic energy. Therefore, internal energy of an ideal gas is entirely the kinetic energy of its molecules. There will be no such contribution of potential energy, since the potential energy will be 0 here as we take an ideal gas. So, what happened? Since the average kinetic energy per molecule of the gas, since the average kinetic energy per molecule of that gas, of this ideal gas, is half n k T. From law of equipartition energy, it will be half k T. For n number of molecules we take n, since n is the degrees of freedom, it will be n k T. Here I write n is the number of degrees of freedom, n is equal to number of degrees of freedom, and K is the Boltzmann constant and T is the temperature, as we know. K is the Boltzmann's constant, T is the absolute temperature. Hence, the internal energy of 1 mole of gas is, internal energy of 1 mole of gas is U is equal to N into half NKT. NKT. This is the average energy per molecule. Then for n number of molecules, it will be N into half NKT, that is the total internal energy of 1 mole of gas. That is half N NKT. N into K, that is Avogadro's number into Boltzmann constant, that gives rise to R, half nRT, as Nk is equal to R, that is the gas constant for 1 mole of gas. That is the internal energy of 1 mole of gas. Now, the molar specific heat of gas at constant volume. The molar specific heat of gas, the molar specific heat of gas at constant volume is given by, that is Cv is equal to du by dt at constant volume, that is d by dt of u, that is half nRT, differentiating with respect to t. So Cv is equal to half nR. Now, since the molar specific heat of gas at constant pressure, therefore the molar specific heat of gas at constant pressure is Cp. Cp is equal to Cp plus R. As you know, Cp minus Cv is equal to R. So Cp is equal to Cp plus R. Therefore, Cp is equal to half nR plus R. Therefore, Cp is equal to n by 2 plus 1 of R as common. Cv is equal to half nR. Cp is equal to n by 2 plus 1 of R. So, the ratio of two specific heats would be the constant. Hence, the ratio of two specific heats that is gamma is equal to Cp by Cv. Cp is equal to n by 2 plus 1 of R divided by Cv is equal to half nR. Therefore, gamma is equal to 2 by n, that is n by 2 plus 1, or gamma is equal to half 2 by n. From this equation, you can see when gamma decreases with increasing degrees of freedom. From the expression, it is clear that indicates gamma decreases with increase of degrees of freedom. Now, this is specific heat of gas. Now, using these relations, we show the examples like what should be the specific heats or gamma for monoatomic gas, diatomic gas, and for triatomic gases. Let me discuss one by one. The examples. First, for monoatomic gas, for monoatomic gases. A molecule of monoatomic gas has degrees of freedom. Here the degrees of freedom will be 3, that is the degrees of freedom. Degrees of freedom, n is equal to 3. Therefore, Cv is equal to n by 2 r, that is 3 by 2 r, and Cp is equal to n by 2 plus 1 into r, that is 3 by 2 plus 1 into r, or we can say Cp is equal to 5 by 2 into r. Here Cv is equal to 3 by 2 r, Cp is equal to 5 by 2 r. Therefore, gamma is equal to Cp by Cv. Cp, that is 5 by 2 r divided by Cv 3 by 2 r, that is 5 by 3, and gamma is equal to 5 by 3, that value is nearly equal to 1.66. In experimentally, the value of Cp, Cv and gamma all are inert, and other monoatomic gases are in close agreement with that of above theoretical values. Again, for diatomic gases, the degrees of freedom is equal to 5, Cp is equal to n plus 2 plus 1 of r, that is 5 by 2 plus 1 r, or Cp is equal to 7 by 2 r, and Cv is equal to n by 2 r, that is 5 by 2 r. Therefore, gamma, which is Cp by Cv, that is Cp 7 by 2 r divided by Cv 5 by 2 r, or gamma is equal to 7 by 5, which is 1.4. The experimental value of Cp, Cv and gamma for many diatomic gases are in very close agreement with that of above theoretical value. These are the theoretical values, but in experiment the values of Cp, Cv and gamma of many diatomic gases are close to the theoretical value. But some cases there is a disagreement in the sense the theoretical value and the experimental value are differ widely or differ much more. Now, for example of triatomic gases, what should be the theoretical result here? The degrees of freedom here is 6, and Cp is equal to n by 2 plus 1 into r, that is 6 by 2 plus 1 into r, that is Cp is equal to 3 plus 1 r, that is 4 r, and Cv is equal to n by 2r, that is 6 by 2r, which is 3r. Cv is equal to 3r. Now therefore sigma, that is Cp by Cv, that is 1 plus 2 by n. The value will be 1 plus 2 by 6, which is approximate to 8 by 6, that is 4 by 3, which is equal to 1.33. The value of gamma is 1.33 here. In case of triatomic gases, a sufficient disagreement is found between the experimental and the theoretical value of Cp and Cv. Here, in case of triatomic gas atoms, a sufficient disagreement is found between the experimental and theoretical values. Of Cp, Cv and gamma. So, with the help of this video lecture, we understand what is law of equipartition of energy, degrees of freedom, and some examples of degrees of freedom, and finally the specific heats of gases, and the condition for monoatomic, diatomic and triatomic gases, the specific heats condition for monoatomic gases, how experimentally these results are found out for diatomic gases, and finally for triatomic gases. So, with this useful and informative notes, let me wind up this session. Thank you.